Okay, tonight's topic is about the fundamental theorem of calculus, and it's basically what I showed you in the last video about definite integrals. It's saying that when we take the integral of something and we're bounded by a region, we go ahead and we take the integral and we take the upper bound and subtract it from the lower bound. And that's all the fundamental theorem of calculus is. All right, and this is a shortcut way to all those. So the limit of a summation is going to be an integral. So it's the shortcut way to all that. So here are a few more definite integrals. That's what we're going to talk about here. So we're going to take the integral from 1 to 4 of 3x to the 1/2. Remember, we increase the power by 1, so it would be to the 3/2 power. And we divide by the new power, which is 3/2. So to rewrite this, it would be 3x to the 3/2 divided by 3/2, which is times 2/3, right? So we go ahead and cancel this out. So our integral then is 2x to the 3/2, and we're going to evaluate at 1 and 4. Remember, we take the upper bound minus the lower bound. That's what the fundamental theorem of calculus says. So we're going to plug 4 in there. When I plug 4 in for x, if we cube 4, we get 64. Take the square root of 64, we get 8. Take that times 2, and we get 16. Minus, when we plug 1, cube 1, we get 1. Take the square root of 1, we get 1. Take it times 2, and we get 2. And then we subtract, and we get 14 for that first integral right there. For number 2, we're taking the integral of secant squared x dx. So we ask ourselves, when we were taking derivatives, what did we take the derivative of in order to get secant squared? If you can remember that, when we took the derivative of tangent, we got secant squared. If you don't, we have a nice little cheat sheet for you as well. So actually, the integral of secant squared is tangent x, evaluated at 0 and pi over 4. Then we plug pi over 4. So tangent of pi over 4, let's see, pi over 4 is 45 degrees. If you remember our triangles, here it was, what, 1, 1, and square root of 2. We'll talk about tangent, be opposite all over adjacent, which is 1 all over 1. So the tangent of 45 is 1, and the tangent of 0 is 0. If you remember what the graph of tangent looks like, we had a asymptote at negative pi over 2, positive pi over 2, which is negative 90 and 90. And it came like this and passed through the origin. So we know that the tangent of 0 is also 0. So our integral from 0 to pi over 4 of secant squared x is 1. All right. Continuing on, I'm going to show you an example with the absolute value. So if you remember back to the last video, we talked about if we had the integral from a to b. So say we have a line a here, and a line b. If we have a point in between here, we can take the integral from a to c and add it to the integral from c to b, and we'll get the same thing. And this is where that comes in. We'll get the right answer. This is where it comes into play, because if you look at the absolute value of something, all right, at one point inside here is going to be negative, and the absolute value is going to make it positive, right? When we take the absolute value, it's the distance away from 0. But at some point, this answer inside here is going to be negative, all right? At another point, it's going to be positive. Well, if we think about, if we make this a 0 and this 2, at what point will it make it negative? Well, okay, so if we go 2x minus 1 equals 0, x equals 1/2. Would you agree if I plug anything less than 1/2 and then I'm going to negative? If I pick 0, I'm going to get negative 1. So we can rewrite this function. If we can go from 0 to 1/2, and we can say, actually, I'll show it to you this way. If I choose anything that's less than 1/2, this function inside here is going to be negative. That's why I put a nice little negative sign out here. So for anything that's less than 1/2, I'm going to have that. I'm going to have a negative value. For anything greater than or equal to 1/2, I'm just going to have a regular positive 2x minus 1. So x is greater than or equal to 1/2. So what I was saying and describing before is we can take these two sections here and add them together. Because we've had to put this negative here, because anything in between negative 1/2 and 0, or 1/2 and 0, is going to be negative. So what we're going to do is we're going to take the integral, and let me get rid of some stuff here, clear some room. We're going to take the integral from 0 to 1/2 of negative 2x minus 1, because it's going to be negative during that interval, and add it then to the integral of from 1/2 to 2 of 2x minus 1, we're going to get, and I forget my dx's there, sorry. Okay, we're going to get our integral, our definite integral. So let's go ahead, let's distribute our negative sign, negative 2x plus 1, or yeah, dx. All right, now let's take the integral. Remember, we increase our power by 1, divide by the new power, and have a negative x squared plus x. And this is going to be evaluated then at 0 and 1/2. All right, and then we're adding to it. Forgot my plus sign up there. We're adding to it. Let's see, same thing. It'd be x squared, positive x squared this time, minus x evaluated at 1/2 and 2. All right, so now we just evaluate this. We take the top minus the bottom. So when I plug 1/2, and then I'm going to have a negative 1/4 plus 1/2 minus 0 plus 0. And then I'm going to have over here, when I evaluate this one, and I plug 1/2 in there. Sorry. Sorry about that. My smartboard will randomly just add pictures whenever it wants to into my paper. So now these are pictures. Anyway, regardless, we're moving on. So I'm over here now to this guy. I've evaluated 1/2 and 0. Okay, so I'm gonna evaluate 2 first. So I'm gonna have plus 4 minus 2 here. All right, minus then a 1/4 plus, or 1/4 minus 1/2. All right. If I distribute my negative sign, so plus a negative plus, all right, I'm going to have, let's see, I'm going to have a negative 1/2 out of these 1/4, so negative 1/2 out of these two. All right, now I'm going to have a positive 1, so plus 1, and then plus 2. So I'm going to have 3 minus 1/2, so I'm going to get 5/2. So 5/2 is the integral of that one right there. And again, sorry that this stuff got all messed up. My smartboard likes to do that sometimes. Okay. The last one here is find the area of the region bounded by the graph 2x squared minus 3x plus 2. The x-axis and the vertical lines x equal to 0 and x equal to 2. Well, we're just going to use the fundamental theorem of calculus. All right. And it's going to tell us that if we take the integral from 0 to 2 of this function right here, we'll be able to find the area underneath the curve that's bounded by the x-axis as well, from 0 to 2. So we'll take the integral of 2x squared minus 3x plus 2. Again, we add the power, divide by the new power, so 2x cubed divided by 3 minus 3x squared divided by 2 plus 2x. And we are going to evaluate that at 2 and 0. When we plug 2 in there, we plug 2. 2 cubed is 8 times 2 is 16. So I have 16 thirds minus 2 squared is 4 times 3 is 12 divided by 2 is 6. 16 thirds minus 6 plus 4. And then minus, when I plug 0 into everything, I'm going to get 0. So minus 0, 0, 0. So no use even writing it out. So I have 16 thirds minus 2. Well, let's get a common denominator of 3 and make this a 6 and make this a 3. So we'll end up with our area underneath that curve to be 10 thirds. Okay? So we just use the fundamental theorem of calculus in order to find the area underneath that curved graph, and so that was bounded by x equal to 2. That became our upper limit, and x equal to 0 became our lower limit, and we were easily able to find the area underneath that without using a summation or a limit of a summation. I hope this helps, and we'll see you in class tomorrow.